In section 6.3, we're going to be looking at another application of integration. We looked at the area between curves, the area above the x-axis before as an application of integration. And now what we're going to do is be looking at volume. Now you might wonder, how are we going to find volume when we only work in two dimensions on the x and the y-axis? And what we do is we take a two-dimensional object and we rotate it about an axis or about a line to produce volume. You'll get into three-dimensional calculations of volume, x, y, and z axes when you get into Calc 3. So in order to find volume, we're going to use a couple different methods. The method that we're going to use in section 6.3 is the disk or the washer method. The washer method is a special case of the disk method. So the idea and the structure is the same, but sometimes we have an inner radius that we need to work with, and we work with the washer method in that particular case. So for the disk method, what we do is we begin with a rectangle and we rotate it about an axis to produce a disk. And the disk looks something like a hockey puck. And that hockey puck has a particular volume. Now what we want is infinitely small disks with an infinitely small width, and we want an infinite amount of these disks. And so we want to get a really good estimate of our volume. So to start this, let's go ahead and look at the volume of a disk. And the volume of a disk is V equal pi radius squared W, width. So pi r squared W. So r is the radius of the disk. Now when we're talking about the volume of a disk and summing these, then it gets to be a little bit different. So let's go ahead and look at a quick picture. If we have a picture of some function f of x, and we want to find the volume, let's say between a and b, and rotate this about the x-axis, and that's what this symbol means, is rotate about the x-axis, what would end up happening is I would take a lot of these little rectangles that I could produce here, and I would rotate each one of them around the x-axis and produce a disk. And then I would add up the area of all these disks. Well, the first thing to remember is with the disk method, and this is very important, for the disk method, your rectangles are always perpendicular to the axis of rotation. We're going to learn another method pretty soon, and those rectangles are parallel to the axis of rotation. So whether they're perpendicular or parallel is important. It makes a difference in which formula that we're going to be using. Now when we talk about rotating it about the x-axis, we can also see that the rectangles in this particular picture touch the axis of rotation. Now that's not always going to be the case. If our rectangles touch the axis of rotation, that basically means we have no inner radius. And the inner radius, we'll get to in just a second, is denoted with a lowercase r. This cap r right here would be the outer radius. It's the maximum value, the height of one of these rectangles. So when we're talking about formulas here then for the disk method, I can talk about, first of all, vertical rectangles. And if I have vertical rectangles, of course, I'm working with dx. So my volume would look like pi. And again, I'm pulling these formulas from right up here, pi r squared w, times the integral from a to b of the outer radius quantity squared dx. Now your textbook also calls this outer radius, whatever function this is, f of x. Okay, but remember it is a radius. Now if we have horizontal rectangles, of course we're going to be working with dy's. So my volume would be the integral of pi from c to d of your outer radius quantity squared dy. Now both of these are basically saying that we're touching the axis of rotation. And remember, my rectangles are perpendicular to the axis of rotation. Now, not all the time will the axis of rotation be the x or the y axis. So then I have to kind of compensate what we need to do with that. And what ends up happening is we take upper minus lower, right minus left, to figure out what is the length or the height of that particular rectangle. Well, we have another situation we need to worry about. What if we're not touching the axis of rotation? So what if the rectangle does not touch the axis of rotation? Well, then we have a little bit different situation. So first of all, let's go ahead and draw a picture of what this could look like. So we could have a graph of, let's say, x squared or something similar. And so this is the region that I want to rotate. Okay, and I want to rotate this about the x-axis. Now, if you note here, I am not touching the axis of rotation. Now, with the disk method, my rectangles need to be perpendicular to the axis of rotation. So we can see here that I have to use vertical rectangles for this picture. Now, it's not just because of the picture, it's also because of the x-axis of rotation. So my volume here is going to be a little bit different. The volume will be pi times the integral, and we'll say that this goes from a to b, just to make this simple. Now, we're used to looking at the outer radius squared minus the inner radius squared in order to get this particular height. So it's going to be the volume of this outer radius squared. So that would be our cap r of x, quantity squared, minus this inner radius squared. Now the inner radius we give a lowercase r. And I have vertical rectangles, so I have a dx value here. Now in this picture, this region right here, all of these shaded regions, those are my inner radius. Those are my lowercase r. The height, this overall height, is my cap r of x. So again, it's my outer radius squared minus my inner radius squared. Now these formulas will be given to you on a test or a quiz, but you'll have to be able to interpret the formulas and be able to apply them to a problem. So having these formulas under our belt, we can start working some problems, and one of the best ways to figure out exactly what the formulas are saying is to work some problems. So let's go ahead and look at our first example. So for this problem, and again, all these problems are very, very similar in the directions, find the volume of the solid formed by revolving the region bounded by the graph of the function f of x equals root 3x minus x squared. That's going to be a parabola opening down, but we're only going to be looking at the positive y values because we don't have the negative values here, this plus or minus, we just have the plus. And the x-axis, so I'm bounded below by the x-axis, but we're only interested in this curve between 0 and 3, and we want to rotate it about the x-axis. So let's go ahead and do a quick curve sketch, and that will give us an idea of where we need to start. So we're only interested in between 0 and 3. So if I plug a 0 in here, I get a 0 back out. And if I plug a 3 in there, I get a 0 back out. And I know it's a parabola that opens down, so I'm guessing that it looks something like this. Now if we want to plot more points, we can. Now I'm bounded below by the x-axis. I'm only interested in this between 0 and 3, and I want to rotate this about the x-axis. So there's a few important things going on here. First of all, we're touching the axis of rotation. The entire graph touches the axis of rotation. So because we're touching the axis of rotation, that means we have no inner radius. So we have no lowercase r. Now because we're using the disk method, we're perpendicular to the axis of rotation. And because the axis of rotation is my x-axis, that means I have vertical rectangles. And if I have vertical rectangles, that means I'm using dx's here. So those are some important pieces of information to get kind of squared away before we get started here. Now if I were to draw one rectangle, it would kind of give me an idea what's going on here. But again, we want an infinite number of these rectangles. Now apparently these rectangles will go from 0 to 3. And when I produce this shape, it's not going to be a perfect sphere. It's going to kind of be more of an ellipsoid. So when we graph this, or when we set up our integral for my volume, I'm integrating pi times the integral from 0 to 3. And again, these are my x values, x equals 0 to x equals 3. Of the outer radius, which is 3x minus x squared, this capital 3x minus x squared is my capital Rx, and that's quantity squared. There is no inner radius dx. So to integrate this, and again, we're not going to overly focus on the integration, you guys can do this. When I square a square root, I just get the radicand back. And when I actually find this volume, I get 9 pi over 2 units cubed, because this is volume. So again, go ahead and go through and verify that's actually your integral. Okay, make sure you can match these solutions. But we're going to focus on setting some of these up. Let's go ahead and look at another example. Now this particular problem is a little bit different. We still want to find the volume of a solid formed by revolving the region bounded by a graph, but now instead of one graph we have two graphs. So I'm kind of thinking this is almost like a upper minus lower curve, kind of like the area between two curves, but then we rotate it, and we're rotating it about the line y equal 1. So to start with, a curve sketch is going to be nice. So 2 minus x squared is a parabola opening down with its vertex at 2. G of x equal 1 is the line y equal 1, so that's the line y equal 1. So what I'm trying to do is to take this region right here and rotate it about the line y equal 1. So a couple quick things. I'm touching the axis of rotation, and when you're touching the axis of rotation, that means you have no inner radius. And that inner radius is known as the lowercase r. We need to make sure that we realize that we're perpendicular to the axis of rotation using the disk method. And because we're perpendicular to the axis of rotation, I'm going to be using dx's because I have vertical rectangles. Now one thing I'd be interested in knowing are these points right here, because when I sketch in my rectangles, it looks like to me that I'm going to start summing them from this point and I'm going to stop at this point. So in order to figure out what these points are, I set my two functions equal to each other. So I need points of intersection. So for my points of intersection, I have 2 minus x squared equals 1. X squared is equal to 1. X equals plus or minus 1. So this is the point positive 1 on this side, negative 1 on this side. And if we were to plug negative 1 into either one of these functions, 2 minus a negative 1 quantity squared, I get a positive 1 back and a positive 1 back, which verifies that this is the line y equal 1. So to set up the volume formula for this, I'd have pi, and I'm going to integrate from x equal negative 1 to x equal positive 1. My outer radius, now this is going to be a little bit more difficult. This is my cap r squared, and it's touching the axis of rotation. There's not a gap between the axis of rotation and the graph. But if I were to plug in 2 minus x squared, that would give me this height, and I don't want that height. I want this big chunk chopped out of it. So this area that's shaded in red needs to be removed in order to figure out your outer radius. So the outer radius is given by your upper curve, so this is my upper, minus our lower curve, and this lower curve is just a fixed value of 1. So that's my upper minus lower. That's my outer radius squared. The incremental width of each of those rectangles is dx. Now there's no inner radius here, and you might say, well, wait a minute, what's this value right here? Isn't that inner radius? No. Inner radius is the distance between the axis of rotation and your solid. And if you notice here, there's no distance between the axis of rotation and the solid, because my axis of rotation is y equal 1. Rewriting this, I get x equal negative 1 to 1. And 2 minus 1 is 1 minus x squared, quantity squared, dx. Now when you go ahead and integrate this, and again you can go through the process, we're more focusing on setting these up. When you go through and integrate this, you can't use u substitution. You can't use u equal 1 minus x squared because du would be a negative 2x dx. I can compensate for the missing negative 2, but I cannot compensate for the missing x. So in order to integrate this, I'll have to expand it, meaning FOIL out 1 minus x squared times 1 minus x squared, and then use our power rule. When you do that, you'll get 16 pi over 15 units cubed. And again, I encourage you to go through and verify that that formula is correct. In our next example, we still want to find the volume of a solid. We'll say that over and over again, but this time we're not going to be touching the axis of rotation with the complete graph. So here we're trying to find the volume of the solid formed by revolving the region bounded by two graphs again. So again, we have like the area between two curves, and then we're taking that area and revolving it between the graph of y equals the square root of x and y equals x squared, and we want to rotate this about the x-axis. So again, the first thing that we'll want is a curve sketch. Now y equal x squared is a parabola opening up, and I know what this graph looks like, and we're going to need to blow up our scale quite a bit to get an idea of what's going on. This is the graph of y equal root x. This is the graph of y equal x squared, and they intersect at 0, 0, and 1, 1. Well, how do you find your points of intersection? You set the functions equal to each other. So points of intersection, set them equal to each other. Square root of x equals x squared. I'm going to subtract square root of x and rewrite it as x to the 1/2. Factor out x to the 1/2, and I'm left with x to the 3/2 minus 1. Using your zero factor property, I get the square root of x equals 0, or x to the 3/2 minus 1 equals 0. Here, x is 0. Here, x is equal to 1 to the 2/3, which is 1. So that's how I get my points of intersection of 0 and 1. Now, I'm revolving this about the x-axis. So, my disk method says I have to be perpendicular to the axis of rotation. Now if you notice here, there's this big gap between the bottom of my graph and the axis of rotation. This is inner radius. So I'm not touching the axis of rotation, so that means I have an inner radius. So I'm not touching the axis of rotation. So that means I'm going to have an outer radius squared minus my inner radius squared. Now again, I'm perpendicular to the axis of rotation. So the axis of rotation is the x-axis, so because I'm perpendicular, I'm going to be using vertical rectangles. And so I'll have dx's here. Now I don't always have dx's. It just seems like a lot of our examples end up being dx's because most of our functions are written in terms of x. So looking at our rectangles here and writing our volume is pi, and I'm going to be integrating these rectangles from x equals 0 to x equal 1. And now I have my outer radius squared. Well, my outer radius squared is this upper curve, which is square root of x, minus our inner radius squared. Our inner radius squared is this lower curve of x squared. Now notice past 1, the x squared becomes my upper. They switch, but we're only interested between 0 and 1, so we kind of have to keep track of that. When we rewrite this, I have pi integral x equals 0 to x equal 1, x minus x to the 4th dx. And again, use your good old power rule, add 1, divide by the sum. Please verify that you get 3 pi over 10 units cubed. That's my volume. So again, setting these up is sometimes the hardest part. Once they're set up, they're fairly easy to integrate. And if you run across any that you can't integrate, well, we can always use Maple to help us out there. In our next example, we're going to be looking at horizontal rectangles. So for this one, we're finding the volume of the solid form by revolving the region bounded by quite a few things actually. Y equal x squared parabola, open up, plus 1, move 1 up on the y-axis. Y equals 0. Y equals 0 is the x-axis. X equals 0 is the y-axis, and the vertical line x equal 1. And we want to rotate all of this about the y-axis. So again, a quick curve sketch is going to be useful here. Y equal x squared plus 1, I'm going to kind of over-exaggerate this a little bit with our scale, is a parabola opening up with its vertex at 1. So this is the point 1. So there's this part of the graph. Y equals 0 is this piece down here. X equals 0 is this piece. And x equal 1 we'll say is this piece. Now if we plug 1 into this function, I get 1 squared plus 1, which is 2. So this point up here is 1, 2. Now we're rotating this about the y-axis, so this is a little bit different than what we're used to. Now, questions we need to ask ourselves. We need to be perpendicular to the axis of rotation. So because I need to be perpendicular to the axis of rotation, I need horizontal rectangles. Now if I'm using horizontal rectangles, instead of dx's, I'm using dy's. So I'm using horizontal rectangles. And I'm just touching my axis of rotation here so I can get an idea what's going on. I realize that most of these lengths I'm not even going to use. So, perpendicular to the axis of rotation, horizontal rectangle. Then I need to know, am I touching the axis of rotation? Well, not all of the solid is touching the axis of rotation. So that's kind of giving me an idea that, I might have to set up a couple different integrals here. And the first integral I see, and again, this is the volume that I'm searching for. This is what I'm going to rotate. It looks like to me from here down, my right minus my left is the same. And then from here up in this blue region, my right minus my left is a little bit different. So I'm going to have to set up two integrals. So my volume, and we'll say this green area below here, will integrate from 0 to 1 because I'm going 0 to 1 here, y equals 0, y equal 1, of my outer radius squared. Well, my outer radius squared here is pretty easy. It's 1 unit. Now the inner radius squared, I'm just going to write it down here so you can see, is 0 because this entire piece right here is touching the axis of rotation. And this is dy because the incremental width of each one of those rectangles is going to be dy. Plus pi integral. Now I'm going to fix this this blue area from 1 to 2. I want to figure out what's going on here. Well, I need my outer radius, which is still 1, but now I need to subtract out that inner radius squared, and of course that'll be dy as this incremental width. So my outer radius is saying this rectangle has a length of 1, but now what I need to do is chop off this piece that I don't want from there. Well, that piece is this curve y equal x squared plus 1. So this piece is y equal x squared plus 1, but we don't want this in terms of x because I'm working in terms of y. So let's take y equal x squared plus 1 and solve. I get x squared equal y minus 1, take the square root of both sides, plus or minus root y minus 1. Now which one do I use? Do I use the plus or the minus? Well, x in this particular case are positive values, so I'm going to use the positive root. So rewriting my volume here, I have 1 dy integral y equal 1 to y equal 2. 1 squared again is 1 minus, now I can replace this x squared plus 1 with root y minus 1 dy. Now when we integrate and evaluate this, and again please go through and verify, you get 3 pi over 2 units cubed. And this is volume. Do take the time to actually integrate these. On a test or a quiz you will need to. I'm just focusing on the setup during the lectures because that's kind of what these sections are about, or volume, not necessarily integration techniques. Our last application problem that we're going to look at involves a sphere with a radius or a hole drilled exactly through the center of the sphere. So let's go ahead and set that up. Okay, for this example we have a perfect sphere and it has a radius of 5 inches. And so if we think about this in terms of 2 dimensions, we could do a quick curve sketch of this. I'm going to make this look as spherical as I can. It's a sphere with radius 5 inches, so this goes 5 to -5, positive 5 up in this direction. And of course it goes in the same region down here, but what we're going to do is we're going to take part of this piece up here and we're going to rotate this, and we're going to rotate it about the x-axis. So we're going to kind of ignore this area down here because we're going to end up producing the same shape when we rotate what's above the x-axis. Now, this exactly is not the rectangle that we're going to be looking at. The rectangle that we're going to be looking at has a hole drilled through it. So what we're looking at is the top half of the sphere, the radius of 5 inches. We're going to drill a hole through the exact center of this sphere that has a radius of 3 inches. So right here, from the exact center, we're going to drill this hole out. So this will be gone. And so what ends up happening is it's going to, again, we're going to kind of visualize this down here, 3 inches down here as well. We're going to have this hole through the center. So this is a perfectly round ball with this drilled exactly through the center. So in order to set this up, we need to come up with the equation of a sphere. Well, the equation of a sphere I'm not really going to worry about. I'm going to worry about the equation of a circle to begin with, and then I'll rotate it. So I get x squared plus y squared equals r squared. Radius is 5, so I get x squared plus y squared equals 25. Now, we know that the radius of this inner piece is 3. And if you think about this, when I cut through here, when I start drilling, all this part of the sphere is going to disappear. Okay, and so I can't say that I'm going to be summing rectangles from -5 to +5. I'm only going to be summing rectangles until I hit this outer point. So in order to figure out what that outer point is, I can plug in 3 for my radius. So I could plug in x squared plus 3 squared equals 25. X squared equals 25 minus 9, which is 16. X equal plus or minus 4. So here's the point 4. Here's the point -4. And again, I'll figure out what the y values are if we need them. And this is kind of the setup that we have. So let's go ahead and look at the volume of the ring that's produced. So again, volume goes pi. X equal -4 to 4. My axis of rotation is the x-axis, therefore I have to use vertical rectangles. And I'm going to rotate these vertical rectangles about the x-axis. Now this entire chunk has to be cut out of the vertical rectangles. So I have an outer radius minus my inner radius. So my outer radius is root 25 minus x squared quantity squared. I'll rewrite that so you can see the negative. Minus our inner radius, which is 3 squared, 3 quantity squared. Vertical rectangles, I have a dx. Now once you run through this one, and again you can integrate this one by hand as well. You don't need Maple or Wolfram Alpha to help you out here. You should be able to do this one. You get 256 pi over 3 inches cubed is the resulting volume. Now I do want to make a quick note. X squared plus y squared equals 25. I need to solve for this in terms of x. So I take plus or minus square root of 25 minus x squared. Now if you notice, this entire region I'm above the x-axis, so I'm looking at the positive root, so that's where this came from. So this is the disk method. It's the washer method when I don't touch my axis of rotation, when I have that inner radius. So these are really fun to set up. You can practice doing all of these integrations by hand to keep your integral skills sharp. You can also plot these in Maple. to get an idea of what they look like. And then we can also check our answers in Maple or Wolfram Alpha as well. But again, you should be able to do all of these by hand. In the next lecture, we're going to be learning about the shell method, where I have parallel rectangles to the axis of rotation. Thank you.